Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm PS Chatterjee, and welcome back to my channel. For my non-civil engineer viewers joining us, feel free to follow along by treating the technical terms as numbers and applying the process to your own projects. In this video, Part 5 of our Excel for IS456 beam design series, we're focusing on the critical aspect of deflection limits and checks. As the graph illustrates, understanding deflection is paramount for safe and efficient beam design. If you're new here, I encourage you to check out parts 1 through 4 to build a strong foundation. In this episode, we'll be deriving the essential formulas to calculate and check deflection limits according to IS456, specifically looking at effective length and the crucial Fs value. Our main goal is to determine the allowable or permissible span for your beam and compare it to the actual effective span to ensure your design is okay. Now the question is, why is checking beam deflection so important? There are several reasons for checking beam deflection. They are as follows. Aesthetics. Excessive sag can be visually unappealing and create a perception of weakness. Functionality. Large deflections can damage non-structural elements like partitions, finishes, and even cause issues with doors and windows. It can also impact services like pipes and ducts. Psychological impact. Noticeable movement can create a feeling of instability for occupants. Code requirements. Building codes like IS456 have strict limits on permissible deflection to ensure serviceability and prevent these issues. Compliance is mandatory for structural safety and legal adherence. In conclusion, essentially, deflection checks ensure that the beam not only has the strength to carry loads but also performs adequately under normal use, preventing aesthetic problems, functional damage, and occupant discomfort. Next. Announcement regarding free Excel sheet. Many of you have kindly emailed me requesting the free Excel sheet. To receive it, please carefully read the description below this video for the instructions. It involves sending an email with your request and leaving a comment on this specific video indicating that you've sent the email. Both steps are required. Once you receive the file, a quick acknowledgement in the comments would be greatly appreciated. This process helps me understand viewer engagement and refine the sharing of this knowledge. Thank you for your cooperation. I want to give a special thank you to Gemini AI, which has provided invaluable assistance throughout the creation of this series, entirely free of charge. Your active support has been fantastic, Gemini AI. If you've found this video helpful, please show your support by liking, sharing, commenting, and subscribing. Let's begin our discussion on the control of deflection as per IS456-2000 by examining Clause 2.3.2.1. This clause states that the vertical deflection limits may generally be assumed to be satisfied if the span to effective depth ratios of structural members are not greater than the values outlined below. These are empirical guidelines that help avoid detailed deflection calculations in many common scenarios. The clause categorizes these basic span to effective depth ratios based on the span length. A. Basic values of span to effective depth ratios for spans up to 10 meters. For a simply supported beam, this ratio is 20. For a continuous or fixed beam, the ratio is 26. For a cantilever beam, the ratio is 7. Here, span refers to the clear span of the beam, and effective depth is the depth from the compression face to the centroid of the tension reinforcement. b. For spans above 10 meters, the basic values mentioned in Part A are multiplied by a reduction factor of 10 divided by span in meters, except for cantilever beams, where deflection calculations should always be performed. Furthermore, the clause mentions that modifying factors are provided to account for the influence of the grade and percentage of tension reinforcement and the percentage of compression reinforcement. In this video, we will focus on calculating the deflection of a single reinforced section. Therefore, our calculations will consider the percentage of tensile steel required and the percentage of tensile steel provided to determine the value of Fs. Next. This slide, labeled Figure 4, Modification Factor Required for Reinforcement, presents a graphical method for determining a crucial modification factor used in structural design, specifically related to steel reinforcement. Understanding this factor is essential for ensuring the long-term performance and serviceability of reinforced concrete structures. The graph plots the modification factor on the vertical axis, ranging from 0.4 to 2.0. The horizontal axis represents the percentage tension reinforcement, extending from 0 to 3%. A series of curved lines traverse the graph, each representing a different service stress in steel under service loads, denoted as Fs, and measured in newtons per square millimeter. The specific values of Fs depicted are 120, 145, 190, 240, and 290 newtons per square millimeter. It's important to note, as indicated in the bottom left corner, that this Fs refers to the steel stress under service loads, meaning the loads the structure is expected to experience during its normal use. Equals to the right of the graph, we find key equations and definitions that clarify the purpose of this modification factor. The primary equation shown is Fs equals 0.58 multiplied by Fy, multiplied by the ratio of AST.REQ to AST.Pro. Let's break down each component of this equation. Fs represents the modified stress in steel. This is the adjusted stress value that takes into account factors like the amount of tension reinforcement provided compared to the amount required. Fy is defined as the characteristic strength of steel. This is a fundamental material property, representing the yield strength of the steel reinforcement specified in the design. AST.REQ stands for the area of steel required. This is the calculated cross-sectional area of tension reinforcement needed to adequately resist the applied tensile forces in the concrete member, based on design calculations. AST.Pro represents the area of steel provided. This is the actual cross-sectional area of the tension reinforcement that is being incorporated into the structural element. It might be equal to, or sometimes greater than, the required area due to practical considerations like bar sizes and spacing and to adjust the design shear stress tau c. Now, let's concentrate our focus on the graph. This graph enables engineers to determine a suitable modification factor. This determination is based on the percentage of tension reinforcement provided, which is plotted on the horizontal axis. By knowing the estimated service stress in steel, denoted as Fs and represented by the curved lines, and the calculated percentage of tension reinforcement, one can locate the intersection point on the graph. From this intersection, you can read off the corresponding modification factor on the vertical axis. This modification factor is implicitly linked to the 0.58 multiplier in the Fs equation we discussed earlier. It helps adjust the allowable stress in the steel to ensure that serviceability requirements, such as limiting crack widths and deflections, are satisfied. Although the formula for Fs involves the ratio of the area of steel required to the area of steel provided, in practical calculations, especially if you've been following this video series, you've likely already calculated and are working with the percentage of both the required and provided steel. Since we are dealing with a ratio, using the ratio of the percentages will yield the same result when interpreting the graph. Most of the time, the calculated value of Fs won't exactly match the values provided in this chart. When this happens, we'll need to interpolate to find both the value of Fs and the corresponding modification factor, Kt. You'll see how this interpolation process works in the next part of the video. In conclusion, this figure provides a vital tool for adjusting the allowable stress in steel reinforcement based on the provided tension reinforcement and the anticipated service stresses, contributing to the safe and effective design of reinforced concrete structures. Next up, effective length and effective depth of a beam. This slide explains the concepts of effective length and effective depth of a beam. We can see two figures here, Figure 1 illustrating effective length and Figure 2 showing effective depth. Effective length. The effective length of a beam is a crucial parameter in structural analysis. It's related to the clear span and the support conditions and is used to determine the beam's susceptibility to buckling. Below Figure 1, we see the calculation for the effective length, LEFF, of the beam. Here, L represents the center-to-center distance between the supports, and B1 and B2 are the widths of the supporting columns or elements. Therefore, the effective length of the beam, LEFF, is calculated as LEFF equals to L minus B1 plus B2, divided by 2. Effective depth. As previously discussed in this series, the effective depth, DEFF, of a beam is the distance from the compression face to the centroid of the tension reinforcement. In Figure 2, D represents the overall depth of the beam, and CEFF denotes the effective cover to the tension reinforcement. Below Figure 2, we see the equation for effective depth, DEFF equals to D minus CEFF. This concludes the explanation for this slide. Next. Continuing our discussion on deflection limits and checks, this slide presents a visual representation of a portion of an Excel sheet where we've applied the principles derived from IS 456-2000's Figure 4. This chart helps us determine the modification factor, Kt, based on the provided percentage of tension reinforcement and the service stress in the steel. On the left, we have a table. The first column, PTPROV, shows the percentage of tension reinforcement, ranging from 0.00 to 3%. The subsequent columns are headed by different values of Fs, representing the service stress in the steel in newtons per square millimeter, 290, 240, 190, 145, and 120. The values within the table are the corresponding modification factors, KT, obtained from Figure 4 of IS 456-2000. On the right side, we see an example where the provided percentage of tension steel, PT Pro, is 0.62%. Say, our calculated service stress, Fs, is 176 Newton per square millimeter. Notice that this value of Fs falls between the tabulated values of 145 and 190 Newton per square millimeter. To obtain a more accurate modification factor for our calculated Fs of 176 Newton per square millimeter, we have performed linear interpolation. You can see the results of this interpolation here, showing the modification factor for Fs equals to 145, the modification factor for Fs equals to 190, and finally, the interpolated modification factor, Kt, for our calculated Fs of 176 Newton per square millimeter is approximately 1.504. This interpolated Kt value will then be used in the subsequent steps to determine the allowable span and check if our beam design satisfies the deflection limits as per IS 456-2000. In the next slide, we will walk through the complete problem-solving process using this interpolated modification factor. Now, let's delve into the method of calculation for our specific beam. We start with the given parameters. The span of the beam, denoted as L, is 9 meters. The effective depth of the beam, DEFF, is 369 millimeters. The characteristic strength of the steel, Fy, is 415 newtons per square millimeter. And the actual percentage of tension steel provided, PT Pro, is 0.62%. The required percentage of tension steel, PTREQ, calculated earlier, is 0.454%. Next, we calculate the expected service stress in the steel, Fs, using the formula 0.58 multiplied by Fy multiplied by PTREQ divided by PT Pro. This gives us a calculated Fs value of 176 Newton per square millimeter. As we saw in the previous slide, this value lies between the tabulated values of 145 and 190 Newton per square millimeter. Therefore, we consider Fs1 as 145 Newton per square millimeter and Fs2 as 190 Newton per square millimeter for our interpolation. To find the modification factor Kt corresponding to our provided steel percentage of 0.62% for each of these Fs values, we perform linear interpolation using the values from the chart derived from IS 456-2000 Figure 4. For Fs1 equals to 145 Newton per square millimeter, the interpolated Kt1 value is calculated as 1.8 minus the product of 1.8 minus 1.48, divided by 0.8 minus 0.6, and multiplied by 0.62 minus 0.60, resulting in 1.77. Similarly, for Fs2 equals to 190 Newton per square millimeter, the interpolated Kt2 value is calculated as 1.4 minus the product of 1.4 minus 1.25, divided by 0.8 minus 0.6, and multiplied by 0.62 minus 0.60, resulting in 1.38. Now, To find the final modification factor Kt for our calculated Fs of 176 Newton per square millimeter, we again use linear interpolation between Kt1 and Kt2, weighted by the difference between our calculated Fs and Fs1, and the difference between Fs2 and Fs1. This calculation yields a final modification factor Kt of approximately 1.504. The basic modification factor for spans less than 10 meters, as per IS 456-2000, is 20. Finally, to determine the allowed span, we multiply the basic modification factor by our calculated Kt and the effective depth DEFF, and then divide by 1000 to convert the result to meters. This gives us an allowed span of 20 multiplied by 1.504 multiplied by 369, all divided by 1000, which equals 11.101 meters. Since our calculated allowed span of 11.101 meters is greater than the actual span of our beam, which is 9.0 meters, the design with respect to deflection limits is considered okay. Now, let's switch over to our Excel sheet to see how these calculations are organized and presented there for the remainder of this video. Serial number 01, checkpoint for start of the deflection calculations in cell A16. Now, we're on the Excel dashboard, looking at the same dashboard I developed for my last presentation. The bottom section of this design sheet is a new area for deflection check and its limit calculations. I'll be added the necessary formulas and a drop-down menu to the relevant cells. First, I created a checkpoint for the start of the deflection calculations in cell A16. Using Excel's define name option, this cell is named as check_05. The Excel formula for check_05, which you can see in the formula bar and I've developed for this demonstration, is equals to, if open parenthesis, n, open parenthesis, check_04 equals OK, comma, ASV greater than 0, close parenthesis, comma, OK, comma, check, close parenthesis. And we currently see OK. This formula means, if check_04, which is the final check for the shear design, is OK and ASV, the area of tensile steel used to control the bending moment, is greater than 0, only then can we begin our calculation for deflection and its limits. Serial number 02, calculations for Fs in cell H16. Our next mission is to find out the value of Fs, in the cell H16. Fs is the key player of this calculation. In the formula box we are seeing the formula, and the formula is, equals to, if, open parenthesis, check_05 equals to OK, comma, round open parenthesis, 0.58 multiplied by Fy, multiplied by open parenthesis, PT_REQ divided by PT_PROV, close parenthesis, comma, 0 close parenthesis, comma, blank quotation, close parenthesis. The name of this cell is Fs, and we are seeing the value of Fs is 176 Newton per square millimeter. Due to cell formatting, we are seeing the unit Newton per square millimeter. The simple meaning of this formula is, if check_05 equals to OK, then give us the rounded value in whole number of 0.58 multiplied by Fy multiplied by PT_REQ divided by PT_PROV, otherwise keep the cell blank. As we already know, Fy is the characteristic yield strength of the steel, Pt_Req equals to the percentage of steel required to solve the bending stress problem, and Pt_Prov equals to the percentage of steel provided. By the zero at the end of the round formula, we are instructing Excel to provide a whole number. Serial number 03, drop-down menu in cell A18. Now, I've created a drop-down menu in cell A18. The name of the cell is beam_type. Following the formula bar, we see 1 cantilever, 2 simply sup, 3 fixed. These represent the types of beams, such as cantilever, simply supported, and fixed or continuous beam. To create this, I selected cell A18, then from the Excel ribbon, I chose the data option, followed by selecting data validation within the data group. In the Allow drop-down, I selected List. Then, in the source box, I typed the text, 1 cantilever, 2 simply sup, 3 fixed. To confirm this, I clicked the OK button. Finally, we can now see the drop-down menu for selecting the beam type. Serial number 03, formula for conditional formatting in cell C18. Moving on to cell B18, this is where we manually input the value for the center-to-center distance of the beam. The name of this cell is L. You can also see two other cells, C17 and C18. Their names are B_1 and B_2 respectively. B_1 and B_2 represent the support widths, and we need to input these values manually as well. Notice that cells B18 and C17 are filled with yellow. Also, observe cell C18, where the digit 0 has a strike through. This visual cue is due to conditional formatting. The conditional formatting rule for cells B18 and C17 is straightforward. If the cell value is less than or equal to 0, the cell will be highlighted in yellow. I trust this conditional formatting is easily understandable. Therefore, I will skip the detailed steps for its creation for cells B18 and C17. However, the condition for cell C18 is a bit different. For a cantilever beam, which has only one support, we're essentially treating the second support as a redundant one for calculation purposes. To manage the visual representation of this in Excel, we've used conditional formatting. We went to the conditional formatting options, selected Use a formula to determine which cells to format, and in the Format Values where this formula is true section, we entered the following formula. Equals sign, open parenthesis, or open parenthesis, and open parenthesis, value open parenthesis, mid open parenthesis, beam_type, comma, 1, comma, 1, close parenthesis, equals 1, comma, $C $18 greater than 0, close parenthesis, comma, and open parenthesis, value open parenthesis, mid open parenthesis, beam_type, comma, 1, comma, 1, close parenthesis, greater than 1, comma, $C $18 equals 0, close parenthesis, close parenthesis, close parenthesis. Think of this formula as a detective making a decision about whether to make something on the screen stand out. It looks at two main ideas, and if either of these ideas is true, it says, yes, highlight this. Let's consider the first idea. First, it looks at the box where you choose the type of beam. It takes the very first letter or number in that box. Then, it asks, is that first thing the number 1? Remember, in our setup, 1 represents cantilever. And also, it checks, is the number in that other box, cell C18, bigger than 0? That box, C18, represents the width of the second support, or B_2, and this part asks if a value has been entered there. So, the first idea is, highlight if you've selected a cantilever beam and there's some width entered for the second support in that other box. Now, let's look at the second idea. Again, it looks at the beam type selection box and takes the very first letter or number. Then, it asks, is that first thing a number bigger than 1? Remember, 2 or 3 represent simply supported or fixed beams. And also, it checks, is the number in that C18 box exactly 0? This is checking if the width for the second support, B_2, is empty, 0. So, the second idea is, highlight if you've selected a simply supported or a fixed beam and the width for the second support in that other box is empty. Finally, the word "or" in the middle means the detective will say yes, highlight, if either the first idea is true or the second idea is true. It doesn't need both to be true simultaneously. Therefore, this formula is making something on the screen change visually when either you've picked a cantilever beam and entered a width for the second support, or you've picked a simply supported or fixed beam and haven't entered a width for the second support. Presently, beam_type is set to 1 cantilever. The center-to-center distance, L, first support width, B_1, and second support width, B_2, are all 0. Consequently, you see a yellow fill in most cells, except for C18. Now, as I change the beam_type to 2 simply sup and then to 3 fixed, observe that all relevant input cells become yellow, and the output cells display N/A, short for not applicable. Returning to 1 cantilever and entering 250 mm in cell C18, you'll notice the cell now has a yellow fill and the text 250 with a strike through, indicating it's not applicable in this scenario. Deleting the value in C18 removes the yellow fill. Now, with cantilever selected, let's set the length, L, to 4 and the first support width, B_1, to 250 mm. Serial number 05, formula for the effective length of the beam in cell D18. For cells D18 through H18, I've used the VLOOKUP formula, with slight variations in the column index number. The detailed calculations will be covered later in the design_02 sheet. Specifically, the formula in cell D18 is, equals to, VLOOKUP, open parenthesis, beam_code, comma, design_02, exclamation mark, $A$3:E$5, comma, 2, comma, 0, close parenthesis. In essence, this instructs Excel to find the effective length based on the beam_code within the range A3 to E5 on the design_02 sheet, and to return the value from the second column. As you can see in cell D18, the effective length for this beam code is 3.875 meters. Serial number 06, formula for the basic ratio of effective length to effective depth in cell E18. The formula in cell E18 is, equals to, VLOOKUP, open parenthesis, beam underscore code, comma, design underscore 02, exclamation mark, $A $3 colon $E $5, comma, 3, comma, 0, close parenthesis. The only difference here is that the column index is 3. As you can see in cell E18, the basic ratio of effective length to effective depth for this beam code is 7. Serial number 07, formula for the modification factor, K_T, in cell F18. The formula for the modification factor, K_T, in cell F18 is, equals to, VLOOKUP, open parenthesis, beam underscore code, comma, design underscore 02, exclamation mark, $A $3 colon $E $5, comma, 4, comma, 0, close parenthesis. Here, the column index is 4. As you can see in cell F18, the modification factor, K_T, for this beam code is 1.768. Serial number 08, formula for the allowed effective span in cell G18. The formula for the allowed effective span in cell G18 is, equals to, VLOOKUP, open parenthesis, beam underscore code, comma, design underscore 02, exclamation mark, $A $3 colon $E $5, comma, 5, comma, 0, close parenthesis. The column index for this is 5. As you can see in cell G18, the allowed effective span for this beam code is 4.567 meter. Serial number 09, formula for the deflection check of the beam in cell H18. The formula for the deflection check in cell H18 is, equals to, VLOOKUP, open parenthesis, beam underscore code, comma, design underscore 02, exclamation mark, $A $3 colon $E $5, comma, 6, comma, 0, close parenthesis. Finally, the column index here is 6. Since the effective length is less than the allowed effective span, you can see in cell H18 that the deflection check for this beam code is, OK. Today, I am concluding part 5 of our series on Excel for IS456 beam design deflection limits and checks. This Excel application effectively summarizes the key design criteria for the deflection check of singly reinforced sections, including, effective length, L_EFF, basic ratio of effective length to effective depth, L_EFF by D_EFF, modification factor, K_T, allowed effective span, allowed_span, and the deflection check, check_06. We've also covered how to bring these values from the design_02 sheet to the design_01 sheet using the VLOOKUP formula in Excel. In the next part, Part 06, we are going to see how to develop a table for L_EFF, L_EFF by D_EFF, and K_T, on the sheet named design_02. I hope you have found this tutorial insightful. Your feedback and questions are most welcome in the comments below. Thank you for watching, and I look forward to sharing more Excel tips with you in the next video. If you found this video helpful, please like, share, and subscribe.